Welcome to Code Club. I'm joined once more by some excellent gophers who are going to help me look at some Go code. Mostafa is here. Hello.
Hello.
Thom is also here. Thanks for joining.
Good morning.
Previously on Code Club, we were doing a deep saturation dive into the Fprintf library, and we found a bunch of interesting stuff, didn't we? So just to recap, we started off with this little program which prints Hello Code Club, and if we dive in to see exactly how that's working, let's take a look. So it turns out Printf is just a convenience wrapper around Fprintf that always prints the standard out. That makes sense. What does Fprintf do? Well, more than you think. It creates this printer object. So we have an object called a PP, which is a little state machine that does the printing, we found out. And having created it, then we call doPrintf on it, and it should then work out how to print everything that you've asked it to print into its little buffer, p.Buff, and it then just simply writes the contents of that buffer to your writer. That also makes sense, doesn't it? So we looked at doPrintf, and we found some goodies in here. So we knew there was going to be some kind of loop, which makes sense. Essentially, the format string that we're processing is a list of what Fprintf calls verbs, like the %s, %d, and those things. It's going to essentially, it starts at the beginning of the string and tries to run forward until it finds something starting with a %. Once it's found it, it then writes everything up to that point to the buffer, because it's just a literal string, nothing special to do, right? Just print it. So in our case, that's the hello. So up to this point, it's all just please print this string, and then we come to the interesting part. So now it's like, this is a placeholder for some data I'm going to give you later, over here. So we have found a verb, so now we're interested to look at it. So the verb could have flags. So what does flags mean in this case? It's essentially the things like modifiers to the verb. So like if you print %v, that will print any value. If you print %+v, that will print field names for structs. If you say #v, that will print a Go literal for that object, and so forth. There's other flags, but we needn't worry about them. Similarly, we have some modifiers about things like, so it doesn't apply to strings, but for example numbers, most of us have used this. You can print fields to a certain width. You can do this with strings too. You can say, print this in a column 10 spaces wide, and truncate or pad it as necessary. Same thing with numbers, and numbers we can print to a limited precision, or a limited number of decimal places. So that's what all of this craft is about, is just processing those. And essentially what we're doing here is we're just parsing the format string. We're setting a bunch of flags on our printer. So we have a p.Fprintf, which is basically telling us this is all the config about how we print whatever it is we're printing, right? It's reasonable. And then we call print.arg. So, this is just a special case for ASCII lowercase simple verbs without precision or width or argument indices, which is the case actually for us, isn't it? That we're printing a string. So this is where we handle the width stuff. So it's not too hard. We could imagine writing this code, couldn't we, if we had to print a certain string, limit it to 10 characters or pad it to 10 characters if we need to. Similarly, printing numbers to precision. So we ultimately get through to print.arg. So let's take a look at this. Okay, so we see the reflect library in operation, which should sort of clue most of us into the fact that something interesting is going to happen. And I think this is about where we got to last time. I can't remember exactly, but clearly, you know, if we're using reflect, then it means we're dealing with things that we don't know the types of. That's what reflect does. It tells us the types of things we don't know the types of. The only time we're ever in that situation is when we have something like an empty interface value. And we normally won't have those unless someone gave us one, so we would never create those. Why would we? We would know what type the thing is, so we could use a real type, and we won't have to use reflect. But printarg clearly has to work for any type of thing, so that's all right. It's a legitimate use of reflect, if I may sound so pompous about it. So we want to... The job that we need to do here essentially is we have the format verb, %s. We're going to look for some data which matches that. You know, if we had 3 verbs here, then we need 3 values to match them up to. So we want to check that we can match them and then do something with it. However, there are some verbs which actually don't need an argument. For example, or rather, we won't be called with such a value. So t is one which will print the type of whatever it is. So essentially, if the argument is nil, you know, normally we wouldn't print that, but there are certain things where nil is a legitimate thing to print, like %v. And we will just literally print nil in angle brackets. You might have seen that. So fine. So let's try and work out what would happen with our program. So this is %big T prints the type of whatever it is. So that's what reflect type of does. Is if you call string on it, it will give you a string such as string. Seems logical, doesn't it? And P will print the address of the object, which can be interesting. Some types can be done without reflection, so we're using a type switch here. Anybody used one of these in their programs? Possibly not, because it's a relatively obscure thing.
I haven't, no.
I've done it when I was doing something badly.
Right. Yeah. I mean, we would hope that we wouldn't have to do this, don't we? Because we should always know what type it is, and so we don't have to do this. But occasionally we do this. So it's a special form of a switch statement, where we say we have some value, in this case arg, and we write dot and type in parentheses. Just this isn't a variable, it's just literally the word type. This is a piece of syntax, and it's saying effectively I'm going to give you a bunch of cases, each of which is some type, like bool. Whatever type arg is, well, that's the case I want you to do. So if arg is a bool, we'll call funct bool, and so forth. So turns out Go has a lot of types, and here they all are. So, well, here are most of them. You probably never used a uint32 or a float32. There genuinely is no reason to use a float32 that I can think of, unless you're on some kind of embedded computer system with a very, very small amount of memory. A washing machine controller, perhaps. Although I'm pretty sure even a washing machine controller has much more memory than my first computer had. That wouldn't be hard. Go has a built-in complex type, which also rarely gets used, but it's there. String is the one we're interested in, isn't it? It's a relatively straightforward one. And we'll see what funct string does. Let's just see what the other options are. one type it can be is a reflect.value, which is like an empty interface type in that it's, you know, could be any concrete type or any interface type. And by having it in the form of a reflect.value, it's easy to do some reflection about it. So, you know, if you have some arbitrary object that you don't know what it is and you're doing some reflection on it and you want to print your reflect.value, it will try to figure out how to print it. So one of the things it might do, for example, is it might have a string method. So you might have seen this if you've created custom types in your Go programs and you want to print them. Of course, if it's some sort of struct, then Fprintf can print it for you in a sensible way. But suppose you have some nice way that you'd like to print it, like you can imagine a contact, somebody's contact details. You could print them as an address label, for example, format them in a certain way. So if you write a string method on your type, and then you call Fprintf to print it, that will be called. Similarly, you can supply a format method, so there's a formatter interface to let types format themselves. That's occasionally useful. So let's look into Fprintstring and let's see what's happening. So, fine. Okay. So now we're interested to know, well, we're printing a string, but how? What was the verb? What are we supposed to do with it? So what options do we have? We have v, which works with all Go values. So now we're in the process of saying, you know, v will essentially do the right thing, whatever the type is. So now we're saying, given that we know it's a string, what's a sensible thing to do with a string? Well, we can set the Fprintq option, that's going to print it as a double quoted string, or the Fprintf option, which is just regular string, no quotes. If it was s, which it is in our case, isn't it? Then we know it's just a regular string, so that's fine. If it's x, then we should print it as a hexadecimal. You know, so like as you know, a string is effectively a slice of byte, and those bytes are usually UTF-8 encoded runes. So, you know, ASCII letters would be encoded as 1 byte each. But if we wanted to print out the actual value of those bytes, we could use %x. And that can be useful. Capital X is just capitalized hexadecimal digits, so like that. And Q, as we said, is quoted string, so fine, and it has to be one of those options. So that has formatted the string. Let's go back to see what's going to happen. So wait, did we actually print it yet? I don't think we printed it yet, did we? Where does it get printed? This is print.arg, isn't it? So that implies it should actually print it, but I didn't.
I think there is a print after this switch case.
Oh yeah. That's the end of the function, isn't it?
Yeah, but I saw the default and I thought it would be another thing, but yeah, it's the same switch.
Yeah. So we're groping around on the seabed here, aren't we? And the visibility is somewhat restricted, as it often is.
Some string must return the. Well, print.arg must just set the value then, right? Or set the format of the arg, right?
Yeah, let's. So it's just setting Fprintf. Oh wait. Yeah, so I thought that was just setting an option, but I think Fprintf actually does something. Let's take a look. It looks like it's going to. I just want to take a moment to tell you about a series of little ebooks I'm writing for Go beginners called For the Love of Go. If you're new to programming or just new to Go, I'll show you everything you need to know to start building fun and useful projects, including tests, variables and values, slices, maps and structs, methods and pointers, and control structures like loops and conditional statements. Go to bitfieldconsulting.com/books to place your order now. And there's a special discount for loyal Code Club viewers. Enter Code Club at the checkout to get 25% off. I hope you enjoy the books. So the first thing we do is we call Truncate String. So if we had set that precision option that we talked about, this is where it would get applied. We can imagine what this would look like, but let's just see. So if precision has been set at all, then do something, otherwise don't do anything. Get the precision that was specified. Iterate over the string by runes. So this is what range does with the string. Is I will be the successive rune numbers, 0, 1, 2, etc. Decrement n. So let's say, suppose precision was 10 for the sake of argument. It isn't, but it could be. So we would decrement that to 9. If it's negative, return a slice of the string up to but not including I. And so we essentially count down n to the point where it hits 0, and then we return up to how many runes in the string are. So it's not as simple as it feels like it should be as simple as just returning a slice of 10, doesn't it? Like if the precision is 10, just return the first 10 characters of the string. So I think the reason they've done that is these bytes are not the same as runes, right? This might have bitten some of us at different times. So actually I got this wrong, and I have got it wrong in programs, so this is a good time to mention it, is actually with a string we get runes and rune index addresses. How do we want to say this? So like, suppose the string only consists of single byte runes, which it happens it does, Ascii characters. So in fact it makes no difference there. So I will be 0, 1, 2, etc. But suppose one of those runes is a multi-byte rune. Like, suppose this was in Chinese instead of English, and we said Ni Hao Code Club, and these would be multi-byte characters. So suppose the first character was 4 bytes in size, which it could be. So the first I would be 0, so that's the byte address of the first rune. It's at element 0 of the string. And then the next rune we get would be byte address 4. So the first rune would occupy bytes 0, 1, 2, and 3, and then the next one would be element 4. So that's why we have to compute it like this.
And this is so awesome that I always considered why the Go tour use a Chinese hello world.
Right.
In the first page.
Yeah.
And now I know why.
Yeah.
I mean, never knew that.
Yeah, it's a nice demo for Go, because if, in other languages we often have to do some special work or use a special type of string or something in order to have multi-byte characters. But it's just assumed in Go that all strings will be UTF-8 encoded Unicode, which is nice.
I'll have to return to the chapter 1 of my code club and mention that.
Right. Yeah. Perhaps it's a good time for you to mention your own code club, a successful spin-off series, isn't it?
Yeah.
So just say a word or two about that.
You mean now?
Yeah, so you have in fact organised and started Code Club Brazil, haven't you?
Yeah, yeah. So I just had, because everything that I've been learning here, it's invaluable, and I wanted to give the opportunity for people that um, doesn't speak English or for some reason doesn't can't participate in this code club to also learn. So I've talked to John and asked if I could borrow his idea and do the
Yeah,
same
I
thing.
don't have the copyright on it.
And I've started, and we have about 100 people there. Of course, less than 20% participate in the meetings, but yeah, it has been fun. I've started with a game, a bingo game that I use it to like give a copy of the three books of John's book for the people that gains the game.
Yeah, what better
And
price could there be?
right, and we built a bingo game from scratch, and we did I forgot how the word in English, but uh, it's not it's not drawn. When you give something, we played the game,
Yeah,
and I gave the books of John for the winner, and after that we had started the go tour. Um, like we are going to the go tour in our meetings.
nice. So that's, it's nice to see that the idea is sort of taking off, and code clubs are springing up everywhere. So if you're a Portuguese speaker, or you just prefer to listen to Thiago for a while instead of me, how can people contact you to join the code club?
Um, you can send a message on LinkedIn, on Twitter. My username is Thiago, Nache.
Fine, I'll put the
Uh,
link in the video comments in the
okay,
description.
or just access the Slack, Code Club Slack, codeclubbrazil.slack. I'll give you the URL, John,
Great.
and we go from there.
Yeah, that's cool. And if anybody is interested in starting their own code club, you don't need to clear it with me, but it'd be nice to hear about it, and we can publicise it on here, so do get in touch. So, yeah, this is interesting, isn't it? Because it sort of seems like the kind of thing that is super trivial, and it's fairly trivial, but nonetheless, it takes a little bit of thinking, and it's a nice reminder about the difference between runes and bytes, which is important. So let's go back to, where did we come here from? Let's go down again. So we're in doPrintf. And we called printarg. And then we called Fmt_string. And then we called Fmt_s. And we called Truncate String, and we've done that, so now it's truncated to the right number of runes. Now we call pad_string. So again, this is like if truncating the string is helpful if it was too long for the width. If it wasn't long enough, we'll need to add some extra spaces, either on the left or on the right. So this is one of the flags that we can use. Is a minus flag will left pad. Otherwise everything is assumed to be left aligned with right padding. So we needn't go through every bit of that, because we understand what that does. Except, yeah, so this is the bit where we actually do the printing, so we should look at this, shouldn't we? So we know something's going to end up written to buff, because that's how it gets written to the writer. So here it is. Here's where we write to the buff. So it could be a good time to take a look at the buff and see what it is. We could have used a bytes_Buffer, which we probably would normally use in this situation, wouldn't we? But they commented here to say we didn't want to have to bring in the whole bytes library just for this one thing. So in effect, they've re-implemented bytes.Buffer, and you know, it's pretty common to see this kind of thing in tests, for example. Or you could think of this as something like a mock, isn't it? It looks like a bytes.Buffer, acts like a bytes.Buffer, but we don't actually have to import that type. So you see this a lot in the standard library, because think about it, you know, everything you want to do in the standard library, if you used the standard library to do it, every package would have to import every other package, and you're not allowed to import cycles in Go, which frustrates some people, and that's largely due to the desire to make compilation fast. But in practice, I find, you know, maybe I'm too much of a fanboy here, but a lot of the restrictions in Go that are really due to making life easy for the parser and compiler writers actually end up, I think, forcing you to be a better engineer, or to write code which is clearer, simpler. You know, we can't do complicated things in Go, so we have to do them in a simple way, and that's great, because simple code is the most... if you have to read someone's code and find the bugs in it, you'll be praying for it to be simple, and in Go it's more likely to be, which is nice. And I think clearly, you know, I have completely drunk the Kool-Aid, haven't I? Like, by the when you first start programming in Go, we all bump up against a lot of annoying restrictions and missing things, or things that just seem weird and arbitrary, and indeed they are. And you complain about them a lot on blog posts, and some of them get high up on Hacker News, and everybody says, you know, Go is useless, it'll never catch on. And they go back to doing whatever it is they were doing. Meanwhile, people seem to manage to write stuff in Go that works. So, fine, I'm rambling. Let's just see how this works. So suppose we had to write a bytes.Buffer. Could we do it? I feel like we could. What would we need to provide? We'd need to provide a write method. So we're basing it on slice of byte, which makes sense. So a write method would take a slice of byte and append it to whatever's already in there, and that's exactly what we do. It's a pointer method because it needs to modify the buffer. So this is something we've spoken about before, isn't it? Anytime you see a method where its receiver is a pointer because it has this star, that's actually telling you, hey, this method is going to modify the thing. And if that's not there, it won't be able to. So, would anybody like to try to deconstruct this and say how it works?
Ask a question about it.
Yeah, ask away.
So since B is a pointer, when we place an asterisk in front of a pointer, that means, hey, you know, let me do stuff with the actual copy of this thing. With the, you know, don't use the pointer. Give me a reference directly to the object instead. Yeah,
that's exactly right. So the pointer itself, we looked at this in a previous code club, and we said, what actually is that pointer? Like, what's its value? And we printed it out, and it was a long hex number, which is actually a memory address somewhere in my Mac, which is where the contents of that variable are stored. And sometimes we want to do things with the pointer, but actually usually not. We're usually just interested in what's the pointer pointing to. Give me that. So that's what the star does, as Thom said, is technical term is dereference it. You know, B is a reference to some slice of byte. Well, give me the slice of byte. Okay, I have it. Yeah, and then what was your question, Thom?
Well, I guess as I've read through the function, I think I understand. Append requires a slice,
Yeah,
not a pointer to a slice.
yeah, that's
So,
exactly right.
so therefore, that's what we're doing here. The pointer we have still points to whatever this is. We're just saying, hey, um, you know, where this thing is pointing, this thing itself, change it. The pointer still is valid.
Yeah, exactly. So we can't append anything to a pointer. That makes no sense because append only applies to slices. So we get the slicer byte that B points to, and we call append, and we pass it the slice that we already have. Might be empty, or it might have some bytes in it, we don't know. And then we pass it the slice that we would like to append to it. But there's one slight wrinkle, which is that you can't append a slice to a slice. What you can do is append one or more elements to a slice, isn't it? So, if you had the number 1 and you wanted to append it to a slice of int, you would just say append x1, that's all right. But now if you had a slice of ints, 1, 2, 3, you can't append that slice to x because it's a slice of ints, not slices, for example. So, you could imagine if you had a slice of slices of ints, then a slice of int is exactly the type of thing that you could append to it. I'm conscious that I'm not making matters clearer, but that happens a lot. So my point here is that we need to unroll this slice into its elements, and we have the magic 3-dot operator, which takes a slice and gives you a bunch of elements. And append will turn it all back into a slice again. So that's great. So that's write, and write string is exactly the same, because a string, for our purposes here, we can think of as just an arbitrary byte sequence. Those bytes will encode Unicode runes, but that's okay. We don't care about that. We don't need to worry about runes here, because we're just literally copying all the bytes into our buffer. Write byte, well, that's easy. It's just the same, but we don't have to unroll it. Write rune, well, this looks interesting, doesn't it? Why is this a lot longer than we might have expected? Anybody care to take a stab at this? I have absolutely no idea, by the way, so we'll find out together.
Seems like the size of the rune might be variable, right? The byte size of the rune, maybe?
Yes, that's an important thing to think about. So if we didn't know, what we needed to do, and we just said, right, your job is to implement the write rune method, you can say, okay, well, clearly we can't just append that rune, because we're not appending it to a slice of rune, we're appending to a slice of byte. So we need to turn that rune into its constituent bytes. So how might we do that? The first thing is, there is, as we were saying earlier, Ascii characters, like the letters, numbers, symbols on the keyboard and so forth, they are traditionally encoded in ASCII, so values 0 to 255 represent these characters, and it turns out UTF-8 is exactly the same. So, they thought ASCII works, everybody knows it, so let's keep that. So if you have an ASCII rune, its UTF-8 encoding is simply its ASCII value. And there is some maximum code point value for ASCII characters, above which, if your rune number is higher than this, then it's a multi-byte rune, effectively. That's what rune self is for. So it's 128. So actually anything higher than 128 is potentially a multi-byte rune. I don't know the details, but I've come across rune self before. So, all right. Let's focus our brain power on it. So we're saying if the rune is less than rune self, so it's one of these single byte runes, what do? We append to the BP precisely the byte value of R.
We
So
do the same as we do for the others, right?
yeah,
Just
that,
depend.
that's right. It's if this if statement is true, then we know it's just a byte. So we can do a regular byte thing. We just have to do the type conversion here explicitly. So okay, so if that's not the case, we know it's a multi-byte rune. So what do? We get the buffer. We take the length of it, and we say for n plus UTF-8 UTF max is greater than cap of b. This is the kind of terse but effective code that you get in the standard library a lot. So let's see if we can figure it. So first of all, what's UTF max? It's 4, so I'm guessing that's the maximum number of bytes a Unicode rune can be, right?
But we said this 128, no?
That's the maximum rune value,
Oh, okay.
which can be squashed into 1 byte. So I think it's something like if it's higher than that, then you need to set some bit to indicate that more bytes follow or something like that. But I'm way out of my depth with that. Thankfully, I don't have to know how UTF-8 works. But so UTF max is saying this is the most bytes that will ever be required to encode any Unicode character. And in fact, all of the 4 bytes are not used. There's nowhere near that many Unicode code points. So fine, so n is the length of it. So the length of the buffer plus 4, is it greater than cap of b? Now what's cap of b? Anybody know? If you're a green belt from BIT, you should definitely know this because you'll be an expert on the Go spec, which includes the built-in functions such as cap. But just in case we don't know, it turns out cap is a bit like len, except that, you know, an array or a slice has a certain length, which is how many things are there in it, but it also has a capacity, which is how much room does it have. So
yeah, I was afraid. I was thinking that was that, but I wasn't sure.
I knew you knew. But there's a difference between knowing and having the confidence to publicly announce, hey everybody, it's this.
Yeah, it's
and
going to YouTube, you know.
And then be wrong. So yeah. It's you know, it's I don't think I've ever called cap, and I doubt anybody here ever will, but very occasionally it's useful. So we're saying if... So what this expression is saying is, do we have more bytes here than we have room left in the capacity for? So suppose you've got, you know, a slice with a capacity of 3 bytes, and we want to write a 4-byte rune to it. That would actually, you know, overflow the end of the slice. So what could we do is we could append 0 to it. Not totally sure what that's about. Could it be
any character, right? Just to increase the size of the capacity of the
yeah,
slice.
that's my guess as well. We know that slices will grow dynamically as you append to them. But then I wonder why we can't just append the bytes to it and have it grow dynamically. So let's see if we can see if this throws any light on it. So we're going to call UTF-8 encode rune. So what does that do? So it takes a slice of byte and a rune, and it says, please write into that slice the bytes that encode that rune and tell me how many you wrote. So that's essentially the job that we needed to do, isn't it? Given a rune value here, what are the 1, 2, 3 or 4 bytes which correctly encode that rune? And here's where we do that. So the place we're asking it to write to is a slice expression on B. So from n, which is, it's the length of the slice, but it's also the index of the first of the next element, isn't it? So you know, if the slice is 3 elements long, then index number 3 will be the index of the next element if we added one to that slice. So we're saying from 3 to potentially 3 plus 4, encode that rune into it. So that's why we do this, isn't it? Is we're saying, let me just graffiti this by kind of I find it's helpful to visualize what we're talking about. So suppose B is this slice, you know, 0, 1, 1, like this, and we have some rune that we want to append to B. We're going to turn it into bytes, so that may result in 1, 2, 3 or 4 bytes being required. Suppose it's 4, and suppose that exceeds the capacity of this slice. We will need to, because we won't be appending would cause the automatic growth behavior, but encode rune just wants to write to an existing slice. So we have to have allocated that memory, if you like, for that to work. So first time round this, yeah, that will be bigger, so we append a 0 to it. So now it looks like this. Okay, is it big enough yet? No, so this loop keeps on looping. Let's append another 0. Is it big enough yet? No, let's append another 0. Let's suppose it is now big enough. So now we're going to ask encode rune to overwrite these 3 bytes. That's what we're doing, isn't it? We're appending enough placeholder bytes, enough zeros, to make room to print the rune into, if you want to think about it like that, and then we're printing the rune into it. And then what do is we calculate a slice expression on that from the first element up to n plus however many bytes it actually was, so up to the end of the new slice. And
so the original length plus the bytes we added.
Yeah, exactly. And so this was our, we were working with a copy of that slice effectively, and now we've updated our copy by writing the runes bytes to it, and now we copy that back over BP. So whatever BP pointed to before is lost, and it's replaced by our new array with these bytes in.
Is there a reason why they wouldn't use make instead? You can set the capacity of your slice with make.
Yeah.
So instead they could have just said, hey, I know that what I'm going to write is n plus UTF 8 dot, or like I should understand like the capacity of what I'm going to write in some way, shape, or form. Should I instead go, you know, I'm creating a new slice anyways.
Yeah.
Why not just do a make? And that is seems clearer than this.
Yeah, that's absolutely right. I think that would work. We could say something like n plus UTF max, make a slice with the same capacity as B plus that number. So maybe that isn't necessary, in which case we'd have done an array copy for no reason, right? So that's only required if we exceed the capacity. So that's the first thing. And the second thing is because make creates a new array, we would then have to copy
Yeah, exactly. That
our
was
existing
my
buffer
guess.
into it.
The overhead of the memory copy of the array
Yeah,
these days.
and
It
I
would
agree
use
with Tom that
memory. Yeah, it would definitely use more memory, no question, to do it.
yeah, I agree with Tom that that would be clearer about what it's doing, and we would definitely prefer that in all our, what should I say, user level programs. If we're not writing the standard library, we probably would do it exactly that way. But the special constraints on the standard library that we talked about before are partly that it needs to be very high performance, so we don't want to do any unnecessary function calls or allocate any unnecessary memory. And readability doesn't matter in the slightest, because, it's like that famous comment in the Unix source code, you are not expected to understand this.
Yeah.
As it turns out, we do understand it because we're smart, but it took a non-zero cognitive effort to figure this out, didn't it? And the point is, we normally wouldn't need to make that effort unless we're just interested, as we are. So it's perfectly alright to write the most insanely convoluted and complex code because it's 1 nanosecond faster than doing it the obvious way. So never do that unless you're writing the standard library, which is possible. So interesting. So that's how the buff works. And we looked at the PP and we saw it's got the buffer that we understand now. It holds the current piece of data, and it has a struct which holds formatting flags and width and precision. There are some other knobs here that you can tweak. So reordering, you can say, this is what I flaked out on last time, and then I looked it up afterwards, is in your format string, so you can say, like, suppose you had, 2 arguments here. You could say, suppose you say, hello X, you are 12 years old. Now, as we said, normally each of these would map to the corresponding data value, but you can go out of order if you want to. So you can say, let's say for whatever reason I just want to print the data in the opposite order to what I have it, and I can do that by saying, I think, element 1, so it looks like a slice index. Apparently that's wrong. Is that just a number?
Declaring both, right?
Sorry, say that again.
You need to declare on both
Yes.
options.
Yeah, I'm sure that's right. Yeah, that's happy. Yeah, so please use this verb to print data value number 2, i.e. the second one I specified. Please use this verb to print argument number 1, and you can do that. Why? I don't know.
I read the spec.
Yeah, that's good. I think it's like those lengthy license agreements that no one reads. It's just like, by clicking OK, you are deemed to have read this legal document. But you are deemed to have read the Go spec, and therefore we should all know this stuff. But clearly, I do not. But yeah, so why would we use something like this? Perhaps we just got given a slice with the data in a fixed order, and it turns out we want to print it in a different order for whatever reason. And of course we could index the slice here and so forth, but it may just be easier to do this. But most likely not. So that's what that one does. And we could get that wrong. So this detects if I did it wrong, which indeed I did. Panicking we already talked about, in that if something panics, then we need to call the Fprintf library to print the panic message, and then if that panics, we don't want to get into an infinite panicking loop. How could that happen? Well, as we said earlier, you could write a string method which will be called by Fprintf to print your value, and it could panic. Shouldn't, but it could.
I think maybe if you use more options than values you have, I forgot, it's not option, but arguments than values, I think it would bring a nil instead of panicking.
Yeah, I think that's right, and it's there is some code to. Let's try and make it do that. So if you specify either too many or not enough data values for the verbs you've specified, that works. So let's run this. Yeah, fine. So let's do that the other way around again. That's it's not a deliberate mistake to make everybody feel better about their programming skills. This is just a normal day's programming for me. So fine. So what if we didn't supply enough data? GoLint already is warning us that we don't have enough args. What do we print? It actually puts a complaint right in the output. So that's interesting, isn't it? You might think, would you get a compile error, or clearly not. But would you get a panic? That's another option, isn't it? But panicking doesn't really make sense, because it's not like this is unrecoverable. I mean, we can do this. We just can't do that. So rather than bail out and do nothing, it says I did as much as I could, but then I couldn't find anything to put in here. I'll show you what ought to have gone there. Is it ought to have been a %d, because that's what you specified. There's an exclamation mark because it's broken. And the reason I was unable to print it is it's missing. That makes sense, doesn't it?
Yeah, I think if it didn't exist, all the Terraform provides would break. If you run with deflog enabled, man, there is I don't know how much thousands of missing is missing for the printf.
Indeed. So now what if we give too many? Let's just give a 0. Again, GoLint detects this, so that's one of the useful things that lint does.
Like you put in your repo.
Yeah. So actually, another option here is it could have just ignored it, isn't it? Because now we can do everything that the format string asked for. This program written in the Fprintf language has been successfully executed, but there are some unexpected inputs which we could have just ignored, or again we could have panicked or failed to compile or whatever. But in fact what happens is we print out everything we were asked to print, and then we say there was in fact an extra integer value saying, it's not %d because it doesn't know what type of thing it should have been, because the problem is precisely that I didn't specify a format verb. But again, exclamation mark saying something's wrong. What was wrong specifically is that you had an extra argument, and here it is. So that's interesting to know. So I think that's the right thing to do, don't you? Because this code is wrong. So a reasonable approach to take could be to say, well, if the code is wrong, just do as much as we can and ignore the rest. That's not what Go does. In general, Go says, I want to let you know that your program is broken, even though I can sort of struggle by. You have a problem which needs to be fixed, because clearly I'm just suffering brain failure here. This can't be correct. So it compiles and runs but complains, which is, you know, that's a legit option. So when we're thinking about our own libraries as designers and engineers, we can include these tools in our toolbox, can't we? That we can say, you know, ideally the thing we would most like is that incorrect programs should fail to compile. If we can do that, excellent, let's do that. If we can't do that for whatever reason, the next best thing is throw some kind of runtime error, like perhaps panic, but ideally not. We'd prefer to just return an error to whoever's calling our function, right, and let them decide what to do about it.
John, I'm curious. So it's conventional not to check the error that gets returned from printf.
Yeah.
But in this case, if you do, does it return an error?
Yeah, that's a great point. So Fprintf actually returns something. You had no idea that it returned anything, but in fact it does. It returns n an error, just like write, for example. So we talked about the I/O writer and reader interfaces before, and they return this as well. So n is how many bytes it managed to write before running into any kind of error, and whether in fact there was an error. So let's receive them and have a look. And let's see what we get. N was 55, which is probably the length of that, including that. And error was nil, so yeah, I think was that what you were really asking, that like in the event of some problem with the font language program like this, would it return an error?
Yeah, I mean, I suspected it wouldn't, given what they did, right?
Yeah.
Or given one, that it's conventional not to check the error. So what's the point?
Yeah.
Of returning that as an error? And they're probably really reserving that for like, hey, I couldn't write standard out as a you know, what counts as an error, rather than you asked me to print something that I couldn't.
Yeah. That's right, and you know, normally I say to everybody, if a function returns an error, you should A, always receive it, and then B, check if it was not nil. And this is, I didn't do that, so am I a massive hypocrite? Yes. But in fact nobody ever checks the error returned from printf, or indeed the n, right? I mean, that's, you know, but when would you want to do that? Well, so if you're writing to a file, maybe, you know, so if you're fprintfing to some file other than standard out, maybe you ran out of disk space halfway through printing that data, in which case you need to let the user know that you lost their data. And sometimes that's all you can do. You know, you can say, oh, something went terribly wrong and I threw away all your data. Sorry about that. But then at least the user knows, so they can reconstruct that work or whatever. So, and similarly, closing a file or any kind of closer could fail, in which case what that usually means is we failed to persist all of the data that we were supposed to. So it is important to know in that case, but in general people do not check the error from printf, nor is there anything really that we can do about it if there was one.
I would bet there is a test that requires error, they are forcing an error. That's the only reason I can imagine.
Yeah. So, but it's nice to know that you can. So I think that brings us to a close for today, and I think we've sort of completed our deep dive through Fprintf, haven't we? We at least found out how stuff gets printed, which turns out to be a lot more machinery there than I would have suspected. We didn't look at scanning, Funct scanf, which is the opposite. Again, you can supply a little program like this in the Funct language saying, now it's saying this is what I expect the user to type in, or to be able to pass from a string, and then I want you to produce some variables or values which match them. And that is occasionally useful, but I think it's fair to say we do a lot more printing than we do scanning, isn't it? So this was probably the right one to look at. So thanks very much to my distinguished guests for being here. It was very nice to have you, and I hope you'll be able to join us next time. So bye for now.